A lot. Yeah, so welcome back to this second morning session. So I'm Jean Dayan from Soleil in Paris, and it's my pleasure to chair this session, which includes one keynote talk and 4 contributed talks. So don't hesitate to ask questions in the chat if you wish, or raise your virtual hand at the end of the talk. And so in order to save time, let's start immediately with the talk of Mrinmai Mukhopadhyay from the SAR Institute in Calcutta, a place I know well. And his talk will be an X-ray scattering study of the assembly of lipid membrane with the peripheral membrane protein. So please, Mrinmai, you can start sharing your screen and start your talk.
Yeah.
Is it working? Yep.
Yeah. Is it working?
Yeah, yeah, perfect.
Yeah. You can hear me, right?
Yeah.
Okay. Thank you, John. It's nice to have it here in the conference because in this situation, it's very difficult. And although we are all kind of virtually meeting everywhere. So what I'll be talking today is X-ray scattering study of assembly of lipid membrane with the peripheral membrane protein. So basically, it's a scattering studies work in combination with some additional studies, and then we'll be talking about the membrane, lipid membranes, and one kind of peripheral membrane protein, that is spectrin. So let's start. I'm from SAR Institute of Nuclear Physics, Kolkata, India. And let's start from here. And first, I should give thanks to our collaborator, because Rajendra Prasad Giri was my PhD student, and he was one of the main performer of this work. And obviously, Professor Sennal, Abhijit Chakraborty, they are the collaborator in SNP. And then some part of work was done in ChemMat cards with Binoy, and some part was done with Sunny, Larry, Lurio, Sojol, and Sumbu Veda. So basically, it's a combination of 2 works. One part is a little old, and the other part is not published yet, so it's a new work. So let's start with this membrane. So we all know that membrane is a very important part of our life, because the membrane we can have permeable and semi-permeable or impermeable. And we know these things because we have membrane in all our cells, everything we do in chemical analysis or in chemistry, in preparing nanoparticle. We all use filtration and different kind of membranes. So in some cases, we want the particle to move from, let me have my, let me show it. What happened? Okay, let us do this with this one. So we can have membrane, have a membrane where the molecules from one side of the liquid or some gel can move to other easily, or we can have a semi-permeable where basically you can restrict some part of molecule and allow some molecules to move other side. And then we have completely impermeable where you cannot have this thing. And cell, and the living cell has a very unique feature that it can be permeable for some molecules, it can be semi-permeable for some molecules and then completely impermeable for some other molecules, depending on the requirement and environment where it is working on. So membrane, in cell membrane, the self reorganization and or the self assembly of the molecules, and then the reorganization of those molecules within the membrane is very important to have this kind of permeability specification and this kind of selectivity of the molecules. So this is one kind of nature's gift, that the membrane that cell has can act as a switchable gateway and as a because if you inject some drugs now, because of this COVID situation, we all know that how drugs and booster doses of vaccines are important. So if you introduce some drugs and you want that drugs to go in, then you need to have a special kind of arrangement where, or the channels where the molecules can go into the cell and do the perform whatever we are required, that is required for. So that kind of targeted drug delivery and this molecular assembly is very important for this kind of cell membrane studies. And so what we have is that this is a kind of a cartoon that normally in all Google things you can get it. And then we have a membrane of this cell membrane, and which is basically consists of some phospholipids. And this is not the phospholipids only, that can have cholesterol, glycerols, and other carbohydrate, proteins, and a lot of complex things, because its cell membrane is not a simple thing that we generally work with with a polymer membrane or some other membrane in our laboratory. So cell membrane is a nature gift, which is something completely different in characteristics in different environment, and also it has the complexity. So it is very difficult to know how this membrane, which part is acting and how this is acting. So that's why what we do, we instead, okay, let's continue this with this lipids, because these lipids have a hydrophilic part, which is which I basically drawn as a cartoon in a blue color drop. And then we have a long hydrophobic tail. So basically this is a lipid, phospholipid basic structure, where you have a hydrophilic part and the hydrophobic part. And then there is a other part, they can assemble in bilayer or vesicle or this kind of different kind of arrangements, where you can, we can play with this kind of lipids. So as I said, that cell is a very complicated structure, and then membrane is also a very complicated structure where you have a lot of things. But you can isolate actually some lipids, and you can isolate some proteins, and we can individually probe that how these lipids are interacting with these proteins, or how these proteins are arranged, or they are actually controlling the self-assembly of those lipids. So these are very important, not to understand how drugs or other molecules can go in or go out of the cell structure. But you can always argue that the cell is a very complicated structure, and why you are doing this thing with a very simple structure, because we have very limitations of measurement technique, and also because if you invoke too many parameters, then we do not know what is doing what. So that's why we start with this model membrane. We call it model membrane, where we have a lipid bilayer or monolayer or vesicle, and then we add protein one by one to see whether how these molecules are basically interacting and how it is helping us to understand the structure of this self-assembly. So here, what I have done, I have taken two lipids, basically two kinds of lipids, where I'll explain those things, and then I have a peripheral protein, which is spectrin. So these are the basically spectrin, one molecule is spectrin molecule, protein molecule, and another is my lipid, which is DPPC or DMPC or DPP or DMP. So this PC and P is basically the head group that I draw as blue, and DM and DP is basically the long chain that we so basically these are the molecules DPPC and DPP, where you have this kind of long hydrocarbon chain what we have drawn with this curvilinear structure, and we have this kind of a head group which is basically PC or P. So PC is it is terminated with CH2. So basically you have a PC head group is much bigger than the P head group. So in other way, this structure is almost same, only this size of this thing, because it's a hydrogen terminated. So P head group is much smaller than the PC head group. But why we have chosen this? Because it contains almost 85% of the lipid membranes. So basically this PC and P molecules, those molecules basically the major constituent of the lipid membrane. So that's why we targeted these two molecules. And then there is a spectrin molecule, which is a really big molecule, like a polymer chain. And I don't need to go through all these spectrin, these motifs on all these things. So basically it's a alpha spectrin and beta spectrin, and then it combined to make dimer configuration or tetramer configuration, depending on what you were or what you are extracting from. So I have two kinds of spectrin. One is a spectrin tetramer, which is a non-erythroid. Non-erythroid means it is not extracted from the red blood cell, but it is extracted. We call it brain spectrin. So it is extracted from the brain of the brain cells of the brain cells. And this another is the erythroid. So basically it is extracted from the red blood cells. So two kinds of protein I have used. One is a tetramer, another is a dimer protein, and two kinds of lipid molecule, DPP, PC and P. So I can use DM or DP depending on my experimental requirements. So that is not going to change much. But our head group PC and P is basically controlling this whole thing. And so what we have done, our model system, so I can spread these lipid molecules on air-water interface like this. So we can have a monolayer or air-water interface, or we can transfer these molecules on solid supported substrate like on a silicon. Or we can do that on a polymer Poisson substrate. So here the problem is that the head molecules are basically stuck to the substrate. So basically we lose the flexibility of the molecules to move around. Whereas if you deposit this thing on a polymer Poisson, it's a soft target. So basically you can, in some sort of flexibility or the transmissibility, you can maintain and you can do that. So basically these are the model systems that I have worked on. And then we have added proteins in the monolayer or in the case of this lipid bilayer case, or it's a special cell. So there is a water window here. So we can add proteins in there, or we can add proteins in there, and then we can see how these structures are changing or these structures are modified. So what are the techniques we use? So we used pi-A isotherm and monolayer relaxation measurements. And then we did X-ray reflectivity from the film or the monolayer. And we also have done the grazing incidence diffraction. So I don't need to explain those reflectivity and diffraction to this community particularly, because this community is very expert in that area. So first part, so interaction of erythroid spectrin with the phospholipid model bilayer membrane. So why this bilayer? Bilayer basically is the membrane structure, original structure. So what we have done, we have deposited this spreaded this thing on water surface, and then deposited double layer of these lipid molecules, which is coming out of this kind of structure. But we have to remember that this head group part is basically the hydrophilic part. So basically it cannot stay in air. So you have to fill this gap with the water. So we have designed a special cell where we have a Kapton window, and then we have this water molecules here. So, and this polymer is a water soluble molecule. So already it is hydrated. So basically both the surfaces are hydrated, and then we can easily maintain this bilayer structure in this cell. And then we can add spectrins in there and can study how these spectrins is basically changing the structure of this bilayer, or how it is attaching with this monolayer, with this bilayer. Okay, so this is the isotherm. So for those basically who are not familiar with the Langmuir monolayer kind of study, so we have a gaseous phase, and then liquid expanded liquid condensed phase, then it goes to liquid condensed, and ultimately it goes to condensed phase. So it depends on how these molecules are interacting and how they are arranging. Here you can see the tails are completely unorganized, but slowly it is getting arranged, and then there will be at some stage where it is basically completely arranged in a special manner, which is called herringbone structure. And then we can have a condensed phase. Generally, we deposit the film at this phase so that we can maintain this kind of structure in the solid on the solid substrate or the polymer cushion substrate. And also you can calculate the compressibility from this monolayer isotherm. We call it isotherm because it's a pi A, it's a two-dimensional thing. So it's a pi A isotherm we call. And we also can calculate the compressibility from this. So suppose this is my isotherm, and then we can differentiate using this formula and calculate the compressibility of the monolayer. So which gives you this how soft or hard this monolayer is. I'm sorry, I have coughing problem because I just recovered from COVID last week. So next is our experiment. So our experiment is, as you can see, that you have pristine monolayer of PC molecules. And if you add spectrin in there in monolayer, you can see that there is a big area increase. So that means that there is a attachment. So first we have to see that whether that monolayer spectrin is getting attached to the monolayer or not. So this is the first indication that you have spectrins attached to the monolayer. So that's basically the signature of this extra area increase. And then also you can calculate the compressibility, as you can see that these are the two peaks which is absent for the pristine monolayer. So pristine monolayer, you don't have those peaks here, but if you add spectrins, you are basically having the high compressibility region where you can say that the spectrins are getting attached. But here one important thing is that you do not have, this is called collapse. So basically if you compress further, it doesn't change, pressure doesn't change because it's getting, it's losing the two-dimensional structure. And then you are, your collapse pressure is actually some sort of signature of how this monolayer is behaving. And then you can see that the collapse pressure is not, quite a bit of change. Here we don't see for PC, the change is not much, but for P, the change is huge. I have to go fast. So then we deposited this polymer layer, or this bilayer on this polymer. And, and then I have shown this thing on the speaker. So the result, important result part is that, so now what we have done, we have deposited this bilayer, DMPC bilayer on this polymer cushion layer, and then added spectrin. So once we add spectrin, as you can see that the red curve is only the DMPC bilayer thing. And if you add spectrin, you can have a extra layer of molecules, which is basically the signature of the spectrin attachment at the top surface of this bilayer. So basically, in case of PC molecule, we have a smooth layer of PC spectrin molecule on top of this bilayer. But if you do this thing for the P layer, then you don't see this kind of extra layer on top of it. but actually it is a kind of seems like it is not visible. It is not. This pectin is not getting attached, but what we have seen in our study from monolayer, that we have spectrins, but these spectrins in this case, you can see that this is the polymer layer, and the polymer layer this density is decreasing. So one thing we have to remember, that this we are under water. So basically these proteins are very close to the electron density, is very close to the electron density of water. So basically you will not see if it is not arranged in a separate layer like the PC molecule. So that's why we don't see this kind of extra layer on top of this bilayer. But instead of that, in the conjugate, that what he proposed is basically it is like a brass kind of structure. So because of brass, we do not see much contrast between the water and the water spectrin layer. So we don't see a big jump, in electron density, and X-ray is not sensitive to that layer, extra layer. Then we carried on. We basically change this temperature of the DMP bilayer. So instead here, the interesting thing is that the bilayer is, when heated at 50 degrees C, basically it's a fluid phase. When it's a DMP layer moved into fluid phase, then actually we found that there is significant drop of density in the polymer cushion. So what is happening here is a kind of, in PC molecule, these spectrins are forming a smooth layer on top of this bilayer. So that's why we see this spectrin layer on top of this thing. But when you are working with PE molecule membrane, then you have this kind of brass structure. But if you increase the temperature to go beyond your fluid, to beyond gel phase, that means fluid phase, then basically this gets deorganized, and then some part of this brass actually sneak in and then can attach to the polymer below layer, the layer below, and that actually causing the spectrin, the density of this layer to go down. And then we can explain that basically, because of this brass layer, brass kind of arrangements, so this can go in. But in case of this cannot go, because it is forming a smooth compact layer on top of it. So this has significance, because if you think that in cell membrane, so in cell membrane it's a PC and PE composed, both are quite large number of molecules in cell membrane. And then if you have a PC rich domain, then the spectrins basically forming a network kind of thing, which doesn't allow the external molecules or some internal molecules to pass through that membrane. But if there is a brass kind of arrangement, then basically you can have the channels where the molecules can transport. So by organizing the PCP molecules internally within the membrane, actually, we cannot say that how they are organizing, but we can say that by organizing these molecules, actually cell can control the permeability of the molecules through this spectrin skeletal network. So spectrin forms the skeletal network, and that spectrin network, by reorganizing this PCP molecule, we can say that the molecules can actually transport from cell membrane from one side to the other side. So we have continued this thing so there are, I said that there are two kinds of spectrin molecules that I can use. One is the erythroid spectrin, another is a non-erythroid spectrin. So non-erythroid spectrin is a tetramer, and it has the specialty that it is a little bit of rigid. So the blood vessels, these blood cells are, they need to travel through tiny vessels of the human body, or any living thing. But the brain vessels are a little bit of large, and so they can have a little bit of extra rigidity of the spectrin of the skeletal network. So that's why the spectrin, brain spectrin are a little bit of rigid than than this kind of red blood cell spectrin, which is a diamond kind of thing. So we continued this thing like by isotherm measurement, reflectivity, and gazing incidence, depth diffraction measurements. Sorry.
We are, I mean, reaching the time devoted for questions and discussion. So please try to go very fast.
Yeah, okay. So this was done in ChemMatCars far. So what we have done, we have here see the same thing, like we have ER and NER spectrin attachment, and then also we can see the compressibility changes. And then we continued this thing for the PE molecules too, that we have seen that there is a basically also this attachment. But here, important thing is that here this blue curve, which is ER spectrin, has the highest compressibility. But here the compressibility of the virgin PE molecules is the highest, but the compressibility of these two curves is almost parallel, almost comparable. And also you can calculate basically the molecular area changes as a function of surface pressure. And you can see that PE molecule, it is a continuously decaying function, whereas it is for the PEC molecule, it is basically a changeover from, so where you have a below 15, you have some changeover from one phase to the other. So this is the, I am skipping this because it's time is out. So this is one important thing that what we learned from this thing. It's a decay constant. It's basically, if you allow the monolayer to relax, then you can actually calculate that what is the decay mode of this monolayer. And yeah, this nu, when nu is actually close to nu, actually define you what is the decay mode. And here we can see that this when you add NER spectrin, that means the little rigid spectrin into the monolayer, the monolayer which was basically flexible, which was decaying like this, becomes so stiff. But in this of PE monolayer, you can also see that because the scale is different, so this is also very stiff. But you can calculate the decay constant, and you can say that the nucleation is basically the decay mechanism for this kind of PC molecule, whereas a dissolution of the molecules is and that also explains our brush kind of arrangement. So what we have done GID measurements on this thing, and then we found that there is a little bit of hexagonal to distorted hexagonal to hexagonal transformation in case of PE molecule, where you have a NER spectrin in the monolayer. Whereas in the case of ER spectrin, this kind of still it's distorted. But in case of PC, this kind of arrangement is not there. So we have done these Bragg rod scans, and then we have found the length of molecules which is above the water surface. We incorporated this molecular length into the reflectivity calculation, and actually can determine that where the air-water interface is, and how these molecules are being arranged from at different surface pressure as a function of ER spectrin and NER spectrin. And then we can see that how this tilting and untilting transition is taking place. So similarly, we can do this thing for the DPP molecule, where we have this kind of arrangement. And then we can, if somebody wants, it can go through the details, but I am out of time. So what I am I can summarize here that basically the flexibility and the head group both plays a dominant role in structural organization of spectrin with the lipid molecules. The loss mechanism is very different for PC and PE molecule, but this loss mechanism doesn't change with the protein attachment. And there are tilting and untilting transition, which is actually happening, and that plays a big role in structural reorganization of the molecules. So with this, I like to thank the listener for this talk, and thanks.
Yeah, my Nicolas Schellis from Oxford. So please Nicholas, you can start your talk on investigating model influence on the analytical resolution of neutron reflectivity and start sharing your screen. Is it perfect? Yeah. And so you have 10 minutes plus 5 minutes question.
Can you see the screen fine?
Yeah, we can see the screen, except I do see the actual slide plus the next slide. I guess this is the same for everybody. Yeah, that's perfect.
How about this?
Yeah, good, please.
Great, thank you for the introduction. So I'm Nicholas Shailes and I'm a different student in the University of Oxford. And the topic of my talk is investigating model influence on the analytical resolution of neutron reflectometry, which is a project supervised by Dr. Luke Clifton and Dr. Andrew McCluskey. So after we collect, the motivation behind the project is that after we collect our neutron reflectometry data, there is generally no unique solution for the SLD profile. Therefore, prior knowledge is needed to analyze the data. That is, for example, the number of layers present in the sample. This is due to a well-known problem with specular techniques, which is the phase loss issue. As I mentioned, to combat this, we create a model of which its assumptions dictate our results. And so we also have to do a known way of reducing ambiguity is taking multiple contrasts. Important as instrument time is scarce and an expensive resource, and not taking enough contrasts or taking too many is an issue. And also we have in the literature, we have commonly reported well-resolved parameters, and we need to know whether they are justified. So it is established in the literature that the resolution of the technique depends on the maximum value of Q, and typically the Q values range between 2 and 10 angstroms, which is currently thought to result in a resolution of about 10 angstroms. So anything with better resolution than this can seem suspicious. In these projects, we're using Bayesian model selection, which relies on Bayes' theorem, which is used to update the probability for a hypothesis as more evidence or information becomes available. What you're interested in this case is the evidence which tells us the probability of the data being generated given the model. The reason we're interested in the evidence is that it can be used to compare different models or model assumptions through the relations of evidence known as Bayes factors. Typically, calculating the evidence is not straightforward, but to the rescue came John Skilling in 2004, who came up with a new algorithm called nested sampling, which estimates directly how the likelihood function relates to the prior mass. So this algorithm takes the likelihood and the prior as input, and here X is the amount of prior probability with likelihood greater than the associated L. So loosely, X is the volume with likelihood above L, and the higher the likelihood, the lower the volume. By following this logic, with every iteration, we can find the next point X that corresponds to a higher likelihood. Since we have the likelihoods and the corresponding X values, we can approximate the integral numerically, for example, using trapezoidal rule. So we have the tools to compare different models and parameters values, but we still need a quantitative metric that relates to the ambiguity of our results. So what we came up with is a definition for the analytical resolution of a neutron reflectometry based on Bayesian model selection, which I'm going to adopt for the rest of this talk. So the definition we came up with is that the analytical resolution is the number of consecutive integer values a parameter can take that has a bias factor below 100. And as you can see from the table, anything with a bias factor above 100 has decisive evidence. So please also note that the natural logarithm of 100 is 4.6. And because my figures are going to be in logarithmic scale, and this definition is good at pinpointing the biggest range of values a parameter can take, and the bigger the analytical resolution, the more ambiguous the results are. So now I have the framework. What we need is to put it into practice. And Luke has kindly provided a data set for this project of optimally good data. And by that, I mean a highly reflective sample of a well understood system with multiple contrasts, including spin contrasts. Sorry, that one by itself. So the substrate consists of a silicon layer, permalloy gold, a self-assembled monolayer with a water interlayer and a floating bilayer on top. So for completeness, here is the parameters we use to code up the model. And I want to draw your attention to the area per molecule parameter, which was used to constrain both the sum and the bilayer. And here you can see the plotted SLD profiles and reflectivity curves. The data was fitted using nested sampling, and you can see that it fits quite well. And these plots I show here show the log bias factor on the y-axis and the pair of values it corresponds to on the x-axis. We're looking at the bilayer tail thickness, which is present in 6 out of the 10 contrasts we have available. And we can see that the resolution is between, the analytical resolution is between 3 and 5 angstroms. And generally it improves with the number of contrasts. And it is most ambiguous when we do not have both H2O and D2O contrasts included in the analysis, which matches the common knowledge and is what you would expect. So here we have some preliminary results for the sum head and tail thickness parameter, which are present in all 10 contrasts as they are part of the substrate. As I said, the results are preliminary, but we can see that the resolution appears to be a lot better than the 10 angstrom, but even the 3 angstroms than that the bilayer tail thickness has, and that may be because of the parameter is present in all the 10 contrasts we have available. And another parameter we have started looking at is the water interlayer thickness, which defines the distance between the substrate and the bilayer. So for this bilayer, the resolution seems to be better than half an angstrom, but further investigation is needed. This may be because by varying the contrast, instead of the surrounding SLDs changing, what is changing is the actual SLD of the interlayer. But again, further investigation is needed. So in summary, nested sampling is a powerful tool that allows to calculate the evidence, and we provided a quantitative definition for the analytical resolution based on Bayesian model selection. For the tail thickness parameters, which is what you've looked at predominantly, the analytical resolution improves for the higher number of contrasts, which is what you expect. And we achieve the high resolution that the 10 angstroms claimed in the literature, which gives us confidence that those values in the literature that claim better resolution than 10 angstroms probably are valid. And we have some preliminary results that also suggest that we can achieve higher analytical resolutions that are better than the common knowledge, but further investigation is needed. So for future plans, we intend to change the model, remove some prior knowledge, and rerun the analysis and see how comes along, and start working with more ambiguous parameters. The assumption here is that they're going to have worse analytical resolution, higher analytical resolution. And an example of this parameter is the bilayer head volume. And we need to complete the analysis for what you've started, for example, the interlayer thickness and so on. And it would also be very interesting to gather some more data with the same system on a different substrate to explore the substrate influence on the analytical resolution. And I want to thank my two supervisors, Luke and Andrew, and my funding bodies, and thank you for listening.
Yeah, thanks a lot, Nicolas, for now move to the following talk, which in fact will be a sponsored talk by Xenox, given by Gabriele Cimarusti. So Gabriele, please. I don't have a title, so I can't introduce you any further, but
actually can you hear me?
Yeah, very well.
So actually I'm Sergio Rodriguez. So
so I got wrong information.
Yeah, sorry about that. So
yeah.
I cannot share the screen yet.
Probably
because I think
Nicolas needs to unshare first.
Yes, that's what that's the message I have. So maybe Nicolas,
Nicolas, can you?
Okay,
yeah.
Great. And so can you see my my screen right now?
Yes, it's perfect. Yeah.
With the first slide. Yeah. Okay, perfect. So my name is Sergio Rodriguez. I'm marketing product manager from Xenox, and I will have the opportunity today to present you our latest developments in the field of grazing incidence, SAX and wax instruments for the laboratory, emphasized with some application examples. So here is the outline of my talk. I will start with a very short company introduction. Then I will present some application examples that I picked up from our customers, mainly in the field of block copolymer self-assembly, organic film photovoltaics, and the polymer brushes. And then I will concentrate the second part of my talk on our new development tools for those applications. So first, let me give you a few words about the company. So Xenox, we are a supplier of solutions for the characterization of nanomaterials using SAX and wax technique. So we are originally a spin-off from ILL, founded in 2000. We are now a company employing a little bit more than 100 people worldwide. So our headquarters are located in Grenoble, in France. We have new buildings actually located just in front of the main access to the SRF. And we also have facilities in the US, in Denmark, and a subsidiary in China. And we have been providing small angle and wide angle X-ray scattering systems for the laboratory since 2010, with a large number of SAX wax systems installed worldwide. In terms of product range, we provide different types of SAX wax instruments for the laboratory. So going from the left to the right, you can see the Xeus 3.0, which is our laboratory beamline, which is a highly flexible SAX instrument, with fully motorized configurations and ultimate measuring performance. On the middle, you can see our vertical SAX wax system, which is the Nano Incider, which is a very compact SAX wax system using our latest technologies in the field of microsource and low background camera, and has a capability to perform simultaneous SAX wax using photon counting detectors. And on the right, you can see the biosolver, which is the biosolver, which is actually our dedicated SAX wax system for pharmaceutical applications, which can handle very low quantity of samples. So we also developed since some years our own data treatment and analysis software with an ongoing development of our analysis modules. And from time to time, we also provide some characterization services for companies or academics interested in understanding what SAX can bring to their applications. So now I would like to start with an application example that I picked up from one of our customers. This is a research that this is an extract from a research led by scientists from Dublin University in the field of block copolymer self-assembly, and they were able to achieve the assembly of block copolymers with an ultra-high molecular weight by fast swelling at high solvent concentration. And they achieved lamellar features with dimensions in the range of 100 nanometer. And you have here GSAX measurements performed on a Zeus instrument, showing the appearance of lamellar in plane ordering at concentrations above 0.8. And sorry, those measurements were measured on a Zeus system, and or emphasizing, for example, the one example of applications where you can use GSAX to support the development of advanced nanomaterials. So then I'm presenting another example, which is in the field of organic thin film photovoltaics. So the performance of those devices could be highly sensitive to the molecular orientation and the phase morphology, which can be assessed with GSAX and GWAX measurements. The purpose of this particular work was to actually control the molecular orientation of small molecule OPV devices by changing the length of the end alkyl chain, which is in red, represented here in the formula. And they were able to show that by increasing the length of this alkyl chain, the preferred phase on orientation was obtained. And actually, when manufacturing devices based on blends using such compounds, the compound, the C4 compound, providing the best power conversion efficiency, was also giving a certain morphology in GSAX measurements with a smaller domain sizes. And in literature, this could be this could lead to better exciton dissociation and consequently better power conversion efficiency. So so like to emphasize now that with those laboratory GSAX, GWAX instruments that you have in the laboratory, you can easily change the measuring configuration from GSAX and GWAX and perform these kind of experiments to support the development of this very active field research. And finally, the third example is on polymer brushes. So this is a work that was carried out by scientists from Duisburg University. So they were actually studying the surface roughness correlation in polymer brushes. And they did actually, so surface correlation, substrate roughness correlation means the ability to replicate the substrate roughness in order to get very homogeneous films. And so they did a comparison with various PMMA brushes and compared that also with spin coating films and also evaluating the impact of VPA on those films and using laboratory GSAX experiments. So GSAX can actually be a very efficient tool to tailor and to follow this roughness correlation by following the appearance of this oscillation, these oscillations that you can get in the out of plane scattering line cuts located between the Yoneda peak and the specular beam peak. And actually here is an extract of a measurement that was done on Zeus 3.0 showing this capability. And I would like to emphasize also that with the current laboratory systems that we have, we perform beam stopless measurements, which can be highly advantageous for this kind of measurements. So now I would like to focus my talk on finish my talk on instrumentation part. So this is with a particular focus actually on the Xius 3.0. So this laboratory SAX-WAX system incorporates an in-vacuum motorized detector for fast change of measuring configuration between SAX and wax. So we also have the capability to use a second detector for wax for simultaneous SAX and wax measurements. It's an instrument that, of course, works for both in transmission and grazing incidents. So we have various grazing incident stages to perform mapping, texture analysis, temperature studies, including in environment, gas environment controlled. We have different options for the X-ray sources. Our standard is low maintenance microfocus sources, where you can have actually different energies and you can switch between them. But we can also provide the high brightness metal jet source from Hexilum and combine it with micro sources. And this system also has a very large sample chamber. So this slide is just emphasizing the capability to on a given sample to switch from GSAX to GWAX, and we also have the capability to perform reflectometry using the pixel detectors, and this is actually possible also because of the beam stopless data acquisition that I was mentioning. That also provides the capability to perform reflectivity and the diffuse scattering analysis. So the reflectometry measurement that I was mentioning is just fully software integrated. And as I mentioned, we also have the capability to perform GWAX. So by putting the detector very close to the sample, and we can also have an additional motorization, in-plane motorization to collect very large surfaces. So this is emphasized here with this perovskite GWAX pattern, emphasizing in red the Qmax value in the range of 4 angstroms inverse in copper radiation, using copper radiation. So here is a slide related to the dedicated detector for wax, which can enable to perform simultaneous SAX and wax or GSAX and GWAX experiments. So it has it can go up to 2 theta equal to 90 degrees, and we also have the capability to move the detector in the second direction to study anisotropic films. And this graph is actually emphasizing the surface of detection that you can collect, so around 1/8 of the Hilbert sphere on this GWAX measurement performed on interconnections. And as a latest development, I would like to mention this new auxiliary source that we have been developing, that is actually a focusing source that is placed just before the sample chamber, and this fully motorized to be actually inserted into the incident beam in order to produce a focus beam on the sample. So we can, with this setup, change between the standard collimation, the standard beam used for SAX, and use a focus beam for example, for mapping wax or for GWAX applications. So we have been doing measurements recently showing that we can increase the intensity by an order of magnitude using this setup, due to the fact that we use a focus beam in the incidence plane and are able to concentrate more photons. So, and as a final conclusion, so I was trying to show you that of course we don't have the brightness of synchrotron, but GSAX and GWAX instruments in the laboratory can really support development of advanced nanomaterials. We can also have high data quality because we can count for a long time, as we are using also photon counting detectors. We can have rather short measuring times, of course, depending on the contrast of the samples, in the range of 5. It could be down to 5 minutes in the range of 5 minutes for GSAX, and as you have seen, generalized instruments can now handle SAX, GSAX, GWAX, reflectometry, the automatic change of measuring configurations. And with that, I end my presentation, and I would like to thank you for your attention. And actually, I would like to invite you to come on our booth and use this quite nice Gather application. Unfortunately, we don't have the opportunity to meet you and to be there in Lund, but certainly this is certainly still a great opportunity to discuss. So please, you're welcome in our booth. Thank
Sergio,
you.
thanks a lot. I mean, what you can achieve with talk in this session, which is a talk, so which according to the program will be given by Joran Stan and Andrew McCluskey on behalf of ORSO, which is a very, very interesting initiative. And the title of the talk is Towards a Standardized File Format for Reduced Reflectometry Data. So I don't know who is going to start.
Me.
You.
Yeah.
Good.
I'm Jochen Stahn, by
Please.
the way. Well, I talk about the principal part, and Andrew is going to give an example or an introduction into the Python modules developed for this. Title is clear. We present this on behalf of ORSO, so I have to present ORSO first. ORSO is a loosely organized group of scientists that are somehow involved in X-ray or neutron reflectometry. It was founded about 3 years ago, and the idea behind is that we want to improve the technique of reflectometry through collaboration and creating common platforms and tools. We do this organized in 4 working groups. This is education and outreach, responsible for teaching, maintaining the web pages, so on. Data analysis, which is clear. So several of the reflectometry data analysis software developers are involved there. One group takes care for reproducibility, to check the quality in the end of what we do. And finally, the file formats group. This is what I'm going to talk about now. We try to define a unified and nice file format for reflectometry curves, which can be used in the end by everyone, we hope. We are open, so everyone can contribute, and you can contact us on the internet by the link given below. We have a poster, P90, where you can talk to us, or just contact any of the members of ORSO. So the file format group is a very open group in a sense that it's essentially Max Skoda and me as chairpersons. We try to bring things together, organize some workshops or conference contributions from time to time, and all the rest is rather loosely connected. So their main contributions are always during workshops and conferences, and after that, normally activity goes down. But in the meantime, we are quite far, so we can present now some first results. I show here a list of people contributed in the past, and as you can see, they are mostly European neutron experts and beamline scientists and male. So it's not very balanced. So we would like to have more input from especially X-ray experts, maybe more soft matter, and not only beamline scientists, but also the final users, because they are the ones profiting from what we are doing. The motivation why we do this. This is the header of a reflectivity file. I produce it normally on my instrument, which is Armor at PSI. And it looks nice for the beginning. It's structured, there's a lot of information. But if you look into the details, it's not written anywhere what is measured actually, who is the owner of the file, what sample was measured, even not if it was X-rays or neutrons. And very important, it's a physical data file without units. So there's a lot missing in here. And our attempt is now to make some guidelines and some definitions to improve the situation. the principal considerations. The file should be used by a wide variety of software. It should be reusable, so it should be it should contain the information of interpretation. Everything should be well defined. It should be clear who is the owner, and it should contain enough information to reproduce the file itself from the raw data. In contrast, there are practical aspects. So all this information is not available. And even if it is, how do you get it into the file? We have to take care for old habits and use terms used in the community. It has to be usable by humans. So it must be quite clear from the layout. And it should be open for individual demands and for future developments. And so we have a variety of activities in the file formats project. So we define keywords, we define rules of how to define, for example, units. We make a list of definitions and terms. So what do we mean by saying a certain term? We develop two representations of the file format. The ASCII file format is quite mature. I'm going to show you in a moment. And for the future, more comprehensive binary file format for complex data sets and future analysis concepts. And we program tools for reading and writing these files. Our clientele are users, essentially. They profit from the compatibility of this file format over the large variety of software and from the extra information in the header, so they don't have to look at the logbook every time. Human scientists profit from the data policy and the information flow, so they give more information to the user. And programmers profit from this standardized I/O. The aim of this ASCII representation is mainly that it's easily human readable. This is a very strong constraint for us. And the file is, as commonly used, separated into a header with a defined minimum of metadata, an extended set of optional entries, and rules for extra entries. And it's also computer readable. And the body with 4 predefined columns and any number of additional columns available, free to choose for the user. So this is the overall layout. We have the header. It starts with the hashes, and then the body with the columns. The header is organized in either YAML or JSON structure. It has some sections like data source, reduction, analysis is an option, and columns. And each of them is further separated in subsections and so on. Now, how does this look like? We have a first line defining that's an also reflectivity data file, so it's compatible. This tells essentially the software what to do with it. It tells the encoding and has a reference. And then we start. First chapter is data source, the owner, experiment, and sample. So there's a lot of things written here. So not all of this is has to be in there. So this is the mandatory part and a lot of optional entries, but all these entries here are defined already. We have a reduction part where we refer to the software we used, and even, if possible, a call. So by just giving this entry, you can recreate the dataset. It's also written who is the creator, not the owner of the dataset, but the creator of the reduction file, and a free text possibility to say what corrections have been done. And finally, very important, we define the columns by name. We give it a unit and the description. Description might be important because, for example, the resolution is just resolution doesn't tell a lot. So you can write here, it's a standard deviation of the wave vector transfer resolution. And then it's clear what this parameter actually means. So I'll now give over to Andrew to talk about the OrsoPy package.
Yeah, so one of the things that we kind of worry about as we're like putting forward this idea for a shared file format is that we want people to be able to use it. We want people to be able to use it easily. And so in that vein, we've put together a Python package that, in addition to handling the file format things, is going to handle a lot of different infrastructure and material that or software that we've developed through the Orso collaboration. So at the moment, it can handle the reading and writing of these .ort files, so the shared file format that Joachim's just been discussing. But it's also linked into the Orso SLD database that, if you're interested in, you can go and ask Artur Glavik about at one of the coffee breaks. So this Python package has been put together by Artur and Brian Moranville from NIST, Artur from PSI, Andrew Nelson from ANSTO, and myself. And it's already being used in a variety of different analysis packages and reduction software. So it's already the case that if you were to collect data at PSI or NCNR or the PORIF instrument ISIS, you would receive a file that is adherent to this Orso standard that Joachim's outlined, and the file is actually written using the OrsoPy package. If you're using any of the analysis softwares mentioned on this slide, so RefNX, GenX, Ref1D, or Easy Reflectometry, then you're able to read in these data files. And for some of them, for example, GenX actually offers additional functionality above and beyond what's necessarily available normally. The software is all completely open source and available on GitHub. And so you can go and have a look, and if you're interested, contribute yourself. Using OrsoPy is really simple. It's pip installable. So if you're familiar with Python, there's a Python package manager that you can install OrsoPy from. And then if you're writing some reduction software and you want to take advantage of the functionality of OrsoPy, it's really quite straightforward to populate an Orso data set and then write the file. Once you have your data and your metadata in these Orso objects, it's really just as simple as save the data with some data file data file string, and it'll go away and save the data. So here you can see that there's the part where you need to populate the metadata. That's probably the most resource intensive part, because you need to come up with a way that each of the different required options is going to be populated. But there's a lot of helper functions built into OrsoPy to do that. Reading OrsoPy is actually incredibly simple. It's just one line. So here you can see we import the load data function. We pass to the load data function the name of our data file, and that loads this metadata-rich Orso object. And on top of that, we've also put together some quite comprehensive documentation that's available on Read the Docs. And so if you're interested, you can go and have a look at that as well. Can you go to the next slide, Joachim?
Yeah, and Andrew, it will be time to conclude to keep time for questions.
Cool, that's fine. I'll just briefly make I think there's one slide left, so it's all right. I just want to briefly mention. So obviously there's the kind of standard Orso file format objects, but Artur has actually done something quite interesting in GenX, where GenX is able to output a kind of modified version of the ORT file that includes analysis information from the GenX software. And so that's an example of this here. I think that we can just go to the final slide, Joachim, and you can close out. Yeah.
So just to conclude.
Yeah, thanks a lot. Ben, you still have your hand raised. In fact, related to this one, and will be about the Expanse project, which is a European project, in fact, aiming at making EOSC, which is the European Open Science Cloud services, available for photon and neutron communities. And the talk will be given by Sophie Serment from DAISY.
Thank you very much, Mr. Dayan. So yes, so no need for a further introduction. Let me start directly and just show you. You see my slide, right? That in the contributors we have Andrew McCluskey. So I will try to make a lot of parallels with what you just heard from Joachim and Andrew on also. So what is Expand and what is its objective? So it's a project financed by the Commission in the frame of the European Open Science Cloud. It is also a close collaboration with the PANOSC project that you might have heard of. And the objective of these two projects is to make fair data a reality for the photon and neutron communities in Europe, as Jean just said. And fair, I think you heard of it, but still it doesn't hurt to repeat. It means findable, accessible, interoperable, and reusable. And once this is achieved, open science is possible. So that's why the European Commission financed these two projects to bring fair to the photon and neutron communities. Very briefly, because I think you all know this, what I mean by the photon and neutron communities in Europe. This is on the one hand, the synchrotrons and free electron lasers that you see on the left, that are gathered under the LEAPS initiative, and the neutron sources that are here on the right that are gathered under the LENS initiative. So you will recognize many of these facilities, and most of them are partners either in EXPANS or in PANOSC. For example, MAX4 and ESS are two organizers of the conference, are partners in our project. So the FAIR principles, what do we mean by this a bit more concretely? In order for data to be findable, and this is, you will see a lot of things that were already addressed by the previous talk. Or in order for the data to be findable, we want to assign a persistent identifier to it. We want to have rich metadata, and this metadata has to be searchable so we can find it. Once we found the data, it has to be accessible, so retrievable. That means you can download it, and for possibly a long time. So long-term preservation is one big aspect of accessibility. And if not the data itself, at least the metadata should be preserved in the long term. Then it needs to be interoperable. So once you have accessed the data, you need to understand, to be able to manipulate it. So the standard file format and metadata format is very important, so that you know how to actually read the data. And the next step is that you have the algorithms to reproduce the data analysis that was made on this data. So this is all in the interoperability. And finally, the aim, as I said, is that it's the data, we want it to be reusable. So what is missing for it to be reusable is a license, a provenance, and the use of community standards, because if you don't understand the data, you might find it, access it and be able to interoperate with it, but not reuse it. So if we look at also what they are already contributing to in these FAIR principles, we see that they do a lot. The rich metadata for the findability, the standard file format and associated metadata that helps a lot in interoperability, making available the algorithms to work with the data, and finally building these community standards for reusability. And what on top of this EXPANS will bringing is the unique and persistent identifiers, the fact that we will make this metadata searchable, bits on the accessibility and for the data analysis on the infrastructure too. And finally, a lot of work in the community standards. I'm going quickly because now I will go into more details on this, giving you 3 examples of what we are doing in EXPANS that is useful specifically for surface science, because this was built by a case study that we did together with Andrew. So you will see the links between the Your Science and the projects. So the first example is talking about unique and persistent identifiers and long-term preservation. What we do in the project is make the data policies at our facilities more fair. Because this is the beginning of everything else, and this is what allows us to achieve these things. The second example will be on the federated search API that we developed and how it's helping to search the metadata through the metadata. And the third one will be on the data analysis, the fact that we're making reproducible data analysis pipelines available online. So to go on the first example, I took an example inspired by, as I said, Andrew's case study. So to reference his experimental data and to find it again, what he, for the publication, for a publication, he used the data coming from several facilities. So the ILL, Diamond, and he then manually uploaded a reduced data set to the University of Bath repository, because this enabled him to have a DOI for the whole data set and a landing page with data access for 20 years. So these were two of his requirements, so that he could manually reference in the publication the data that was used. This is already very good, but what we are doing with the data policies in Expanse is that we will make this easier, because each photon and neutron facilities will be minting a data persistent identifier, so which is the more general term for DOIs. And we'll define in the data policy and guarantee the embargo period and the archiving duration of the data. We also want to make the metadata recorded and stored along with data made in the process of the facility, and which means that all PIDs will be linking to each other in a machine readable way. So making all of this process much easier. The second example is on the search. So again, to make the parallel with what Andrew was explaining, how he makes the research, a reflectometry model has parameters and they need starting values. This is a mixture of, as it's written here, sample knowledge, published results, and trial and error. And so what we developed in Expanse that can help in the part of the published results, so that means what has already been made in the community, so that it's easier to pick the starting values, is the span search API, which is one central point that can look into the metadata catalogs of each of our partner institutes and gather the results into a single entry. And this is also, since it's a PAN community developed, it understands the Nexus format, which makes the search features much more efficient. So that means that in the future, Andrew, if he starts again, would be able to search datasets across all PAN facilities, so maybe find more published results on similar experiences, and search on Nexus terms, which means that he will be able to focus on what is interesting for his research. So the right sample, the right environment for the experiment. And also file format that was presented just before is, or at least will be mapped to Nexus. So that means that all that is contained there will be searchable in the search API. And finally, the last example, the online PAN data analysis. So again, with this publication, in this publication, there is a reference to the workflow that was used. So you have the GitHub, there is a DOI, there is also the environment that that is needed to run the pipeline. So really, if someone is going to this, he can download it to his laptop and run the whole algorithm. So that's very good. But it will take 1 day to run because the laptop is a laptop. So here we have the advantage of being able to offer cloud computing for this. And what we do in the project is that we take the services, the Jupyter notebooks or the virtual machine services that are offered by our facilities, and we make them available in the cloud, along with a testing framework to verify that the pipelines are working in the right environment, that with the reference data, it gives the right results. So you make sure your environment is well configured. And on top of this, it is interoperable with the EOS Federated Cloud, which means that even if you don't have an account at one of the PAN facilities, you can still apply for resources and run this pipeline from wherever you are in Europe. Which leads me to the conclusion. We think Inexpand the reflectometry community is an example of going good fair practices. So they use standards, they link the data publication and algorithm together to make for better reproducibility and provide rich metadata for future reuse. What Expand is doing is helping to make these mainstream across all photon and neutron communities and easier by integrating this in the facilities processes. So working on the fair data policies, as I said, the beginning of everything, working on the metadata catalogs and making endpoints to this federated search API, and making the data analysis services portable. Which led me to thanking you for your attention, and please feel free to ask questions or come visit us in.
Thanks.